There are two types of symmetry we discuss with functions. The first is symmetry about the y-axis. If we take, for example, this first graph, we can see that if I choose any point on the left side of the graph, there will be a corresponding point mirrored about the y-axis on the right, and vice versa. If I choose a point over here on the right, then there will be a corresponding point mirrored about the y-axis over here on the left. This kind of symmetry is called symmetry about the y-axis because the y-axis acts as a mirror. This second graph, we can see the same symmetry here. If I start with this point -2, 3, I can see that I have a corresponding point at 2, 3 on the other side. This applies whether I'm looking at a top part of the graph or a lower part of the graph. In all cases, the y-axis acts as a mirror, so that if I count over the number of units that it took me to travel horizontally to the y-axis, I can continue that same number of units until I get to a point on the graph on the other side. We can observe symmetry about the y-axis in numeric data as well, remembering that the y-axis occurs at x equals 0. So in this example here, we see the y-axis at this point 0, 7. Now the 7 isn't important. It doesn't matter what the value of the y-intercept is. What matters is that as we step 2 units to the right, which is really just one box in this case because we note that our x values are increasing by 2 at a time, I get a 5. And if I step 2 units to the left in my x values, I also get a 5. So that this is what the symmetry looks like when I'm just looking at values, right? Comparing that again to the graph, this here would be f of 3 equals 1. On the other side, we would have f of -3 equals 1. So what we can see happening is that as we step the same distance in the x direction away from the y-axis in both directions, we get the same y value, right? We can see that taking another step here as we go out 4 units to the right versus 4 units to the left, I still get the same y value. So if I start to write this out symbolically, here's what it looks like. F of -2 equals 5, and f of 2 equals 5. We can see that this symmetry holds because of the fact that f of -2 is equal to f of 2. The reason I'm writing it this way is that it helps us to understand the basis of our symbolic rule. The symbolic rule for symmetry about the y-axis is that f of -x is equal to f of x for all x in the domain. This is the same thing as saying that the y values, which is f of x or f of -x, are going to be the same as long as our x values are opposites of each other or are the same distance from the y-axis in both directions. So, some examples of functions that are defined symbolically that have that kind of symmetry are here: x squared plus 1, the square root of x squared minus 1, and x to the 4th minus 3x squared plus 5. What all of these have in common is even powers of x. If every single term is an even power of x, then we will have symmetry about the y-axis. Now when I say every single term, I'm including this one, the plus 1. The way that I can see that as an even power is to write it as x to the 0. And 0, if I had to choose whether that's even or odd, I would say it satisfies the definition of even, because 2 divides evenly into 0. It does not leave a remainder. So this is a rule for determining symbolically whether or not a function has that symmetry about the y-axis. The reason even powers have that kind of symmetry, as we can imagine, is that if we just take, for example, f of x equals x squared plus 1, we can say, well, what is f of minus x in this case? Well, that's just minus x in parentheses, quantity squared plus 1. But now I can tell that the exponent of 2 is applied to this negative sign, so that result is always going to be positive, and therefore this simplifies to the same as x squared plus 1, which is the same thing as f of x. We can see that that's the effect even powers have, is that they erase the information of what sign the number was that went into the function as input. And because of this pattern, we would call a function whose graph has symmetry about the y-axis an even function. So an even function does not have to be an even power. There are some others as well. For example, absolute value functions. We know that absolute value functions have a graph that looks something like this, right? If this is a x and a y axis, our absolute value function would be a v that touches down at the origin. This is an even function also because its graph has symmetry about the y-axis. It does not have even powers. But if the graph has this kind of symmetry, then we would call it an even function. The other kind of symmetry that we pay attention to with functions is what's called symmetry about the origin. It's not symmetry about the x-axis. Any graph that has symmetry about the x-axis is not going to pass the vertical line test and is not going to be a function. So if the context is nonlinear functions, then these are the two kinds of symmetry that we're interested in. Symmetry about the origin is a little bit different from symmetry about a line. If we look at this first graph here, we can see that any point on the graph will be reflected through the origin to another point on the graph. Another way of thinking about symmetry about the origin is that if I were to take this graph, the whole thing, and center it, put a pin right here in the x-axis, and spin the graph around that pin 180 degrees, I would get the same graph, right? This point up here would come down to, say, a point down here. This point here would pivot around to this point down here, etc. So this is what symmetry about the origin looks like. If we take a couple of reference points, like for example, let's consider 2, 2. I can see that the reflected point in this graph is -2, -2. So the pattern that we see here is a little bit different from symmetry about the y-axis. F of 2 equals 2. F of -2 equals -2. What I can see here is that when x changes sign, y also changes sign. To contrast that with what happened in symmetry about the y-axis, we could say there that when x changes sign, y does not change, right? Here we see when x becomes the opposite, y becomes the opposite as well. Looking at our second graph, we can see a similar pattern. This point here is at 2, and let's estimate that value to be about 0.8. The corresponding point that gives it symmetry is at -2, -0.8, right? All right, looking at a numeric example, again, here is the origin. This is where we're starting. I want to see what happens when I step 2 to the right in the x direction. Again, my x's are increasing by 2. And I step 2 to the left in the x direction. I can see that I don't have the same y values. What I have are opposite y values. And if I write this out in function language, it looks like this. F of 2 equals -1. F of -2 equals 1. That gets us to our symbolic rule here, which states that if I replace x by its opposite, it makes y get also replaced by its opposite. F of -x is equal to minus f of x, or another way of saying that, f of the opposite of x is equal to the opposite of f of x. We can always interpret that minus sign in front of a number as being the words the opposite of, because it's the number with the opposite sign. So some symbolic examples are written here, and we can see why this rule is satisfied by looking at what happens when we take f of -x. That would be, in this case, -x cubed. Now the power 3, because it's an odd power, it maintains the sign. So this is the same thing as -x cubed. And we notice that -x cubed is the same thing as minus f of x. That's exactly the opposite of f of x. So odd powers, because they preserve the sign, they tend to lend themselves well to odd functions. So odd powers are generally what we're interested in here. But we could also have odd roots. Like, for example, a cube root here. Odd roots also preserve signs. So any function that is comprised of odd powers and odd roots, in which every term is an odd power or an odd root of the variable, is going to have this kind of symmetry. Now, that includes terms like this -2x, because we know that that is really 2 times x to the power 1. So that is an odd power of x. It doesn't matter whether the coefficient is an even or an odd number. That 2 isn't causing any problems at all, as long as every power that shows up on x is a power 1. So note now that if I had a term like a +3, if I had something like x to the 3 plus 3, this would actually not be an odd function, because again, that 3 I have to think of as 3x to the 0, and 0 is an even power, right? So this does not have symmetry about the origin. Because of this close relationship between symmetry about the origin and odd powers and odd roots, we call these odd functions. Anything that has symmetry about the origin is referred to as an odd function. So now we'll get a little bit of practice looking at symbolic functions and classifying them as even, odd, or neither. Lots of functions have neither of these kinds of symmetry. To do this, we're going to look at each term and figure out whether all of the terms are odd powers or odd roots, all of the terms are even powers, or if neither of those is true. Looking at this first example, we have 2x cubed plus x. I'm going to think of that x as being x to the 1. Because both terms are odd powers of x, I would determine that this is an odd function. Looking at the second example, 5x cubed minus 7, I would have to think of that 7 as being 7 times x to the 0. So what we really have is a sum of an odd term and an even term. When we put them together, we get neither. Finally, we have 5x cubed minus 3. Again, I would think of that as 3x to the 0, so that both terms, in fact, are even powers of x, and I can conclude that this is an even function. It can be helpful to look at a graph if we're not sure, right? So I could pull up graphs of each of these functions. Desmos is a free program that you can access from any web browser, desmos.com. You can see the URL up here. If we just type in desmos.com, the calculator is the first piece to come up. I've typed in the function y equals 2x cubed plus x, and I can see from this graph here that it does in fact look like an odd function. The next on my list is 5x cubed minus 7. So making this adjustment, I can now look at this graph and verify that it does not have either kind of symmetry. It looks like it has some symmetry about this point down here at 0, -7. This is the graph of x cubed stretched by a factor of 5 and then shifted down 7. This does not have symmetry about the y-axis or symmetry about the origin. Finally, I have 5x squared minus 3. I'll just change this power here and change this term to a 3. And I can see that I have a parabola stretched by a factor of 5 and shifted down 3. Shifting this graph down 3 units did not affect the symmetry about the y-axis. So this does in fact look like it has symmetry about the y-axis and therefore looks to be an even function. Looking at a table of numbers, now we can go through this exercise also. I want to start by identifying where x equals 0 is. So it looks like we have a y-intercept of -1 in this case. Let's step the same number of spaces to the right and the left, verify that those x values changed by the same amount. So we went up 2 and we went down 2 from that y-axis, and we have the same y in both cases. If we see that every time we do this, we get the same y, then we can conclude that this function is even. Looking at the second example, I'm going to start again by identifying where x equals 0. It looks like this graph passes through the origin. Now I'm going to see what happens as I go to the right and to the left. I can see that here I have opposite y. So because I have opposite y values, that's starting to look like the pattern for an odd function. Because the graph also passes through the origin, this is in fact an odd function. Looking at our third example, I again start by finding where x equals 0. This time it looks like we have a y-intercept of 6. And I step both directions from there, and I see that I get opposite y. Opposite y suggests an odd function, but something about an odd function that we haven't mentioned yet is that if 0 is in the domain, it really has to pass through the origin. This 6 here is going to cause us a little bit of trouble, as we can see from the fact that if 1, 2, 3, 4, 5, 6 were on this graph and it had symmetry about the origin, then it must be true that when we figure out what reflected point is also on this graph, that point would be down here at -6. So if that's true, if it does have a point here that wasn't showing up in my table, then this would not be a function, right? This would fail the vertical line test. So an odd function that has 0 in its domain must pass through the origin. This is actually neither. So this is basically what we're looking for in numeric functions. Start from x equals 0, go both directions, decide whether the pattern appears to be that of an even function or an odd function. If it's an even function, it does not have to pass through the origin. We've seen examples of even functions that do not pass through the origin. If it's an odd function and x equals 0 was in the table, then it needs to have y equals 0 also corresponding to x equals 0 so that it passes through the origin. And that concludes symmetry.